Hello, everyone, and welcome to this week's lecture. This week we're going to discuss Chapter 9, which is on earthquakes in Earth's interior. And I think that this is a good time to be giving this lecture because I'm sure a few of you have been increasingly interested in earthquakes recently, as we've been able to feel some earthquakes in Boise as a result of some earthquakes in the Chalice area that have been greater than a magnitude of 6. So without further ado, let's get into it. So I'm sure a lot of you are familiar with the damage that earthquakes can cause. But before we get into that and what causes some earthquakes to be more violent than others, we need to discuss what an earthquake actually is. It's basically the vibration of Earth produced by the rapid release of energy. And energy that's released as a result of an earthquake radiates in all directions from its source, and the source of the earthquake is called the focus. And energy is in the form of waves in the case of an earthquake, and sensitive instruments around the world record energy in the form of waves that is produced by an earthquake. These instruments are called seismographs. So this diagram shows an example of the focus, also known as the hypocenter, which is the source of an earthquake. And then directly above the focus is the epicenter. So that's the only difference is that the epicenter is the location on Earth's surface away from which the waves propagate through the Earth. And these waves are known as seismic waves. And as you might have guessed, a lot of earthquake activity is generated from along faults as a result of plate tectonic forces. So the example used in this figure is in fact a fault and a slippage along that fault causing the release of energy that causes the earthquake. So movements that produce earthquakes are in fact usually associated with large fractures in Earth's crust called faults. And most of the motion along faults can be explained by plate tectonics theory. So the first person to discover the cause of earthquakes was H.F. Reed. And he hypothesized that rocks on both sides of an existing fault are deformed by tectonic forces. And as rocks on one side of a fault move past faults on the other side of the fault, those rocks bend and store elastic energy. You might think of those rocks as a rubber band in this case. And frictional resistance holds the rocks together most of the time. So even though tectonic forces might be pushing rocks on one side of a fault in one direction relative to rocks on the other side of the fault, most of the time the frictional resistance or the friction between the rocks on both sides of the fault stops those rocks from moving. However, when those rocks do move because there's too much pressure and that resistance is overcome, then that elastic energy is released and seismic waves are created and you experience an earthquake. So when that elastic energy is released, that's known to as elastic rebound, which is the mechanism that creates an earthquake. And this occurs because slippage at the weakest point along the fault, which is called the focus, again, occurs. And then vibrations occur as the deformed rock springs back to its original shape. And that is elastic rebound. Earthquakes most often occur along existing faults whenever the frictional forces on the fault surfaces are overcome, kind of like how we talked about on the last slide. One way to think about the elastic rebound that causes earthquakes is to think about the deformation of a stick as you hold it in your hand and bend it until it breaks. So if we look at the figure on this slide here, let's think that we have a pre-existing fault in the rocks, and before that fault has moved, or before rocks on one side of the fault have moved relative to the rocks on the other side of the fault, you're simply holding the stick in your hand without applying any pressure on it. However, as you move along in time, so if you move one down within that diagram to diagram B, you can see that tectonic forces are forcing rocks on the left side of the fault to move up relative to the rocks on the right side of the fault. So at this time you can think of holding the stick in your hand and bending it, but it has yet to break. Then if tectonic forces continue to apply additional pressure to move the rocks on the left side of the fault relative to the rocks on the right side of the fault, eventually that pressure will overcome the frictional forces that were stopping the rocks from moving. And that is analogous to the stick in your hand breaking because too much pressure was applied to the stick. After the stick breaks, both sides of the stick vibrate as the energy is released quickly and violently. And the same thing can be said for movement along the fault line causing an earthquake. Then finally, after those vibrations cease, the rocks return to their original shape but in a new location, just like the stick returns to its original shape but in a new location. So one of the crazier examples of slippage along a fault line and the new locations of the rocks on one side of the fault versus the other side of the fault occurred in a 1906 San Francisco earthquake that was probably around a magnitude 9 earthquake or greater. And so you can see in this farmer's field here how there was slippage of rocks on one side of the fault relative to the other side of the fault, and what used to be these parallel lines of some sort of tree or shrub in the field are no longer parallel lines. Similarly, if you zoom into a picture of this farmer's fence back in 1906, you can see that the fence is no longer doing a very good job of keeping whatever sort of livestock or whatever was inside the fence because one side of the fence moved about 8.5 feet relative to the other side of the fence. So this is again a great example of slippage along a fault and the new locations of the rocks on either side of the fault after an earthquake occurred. When most people think of an earthquake, they're actually talking about the primary earthquake. However, it's important to know that there are also foreshocks and aftershocks. So aftershocks are adjustments within the rocks that follow a major earthquake and often generate smaller earthquakes. So you can think of the weakest section of the rocks along a fault line slipping, and those rocks on one side of the fault moving relative to rocks on the other side of the fault. But then after that, you're applying additional pressure that's working against the frictional forces at other locations along that fault line. And sometimes it causes other locations along the fault line to also slip and overcome those frictional forces, causing additional earthquakes, which are again called aftershocks. Also, small earthquakes called foreshocks often precede a major earthquake by days, or in some cases by as much as several years. So foreshocks you can think of as smaller slips along the fault line that are sort of building up to a bigger earthquake over time that will be considered the primary earthquake after the series of earthquakes has occurred. Another thing that's really interesting to note here is that it's not actually possible to know which earthquake is the primary earthquake until the series of earthquakes has already occurred. For example, you may have a fairly large earthquake and it just be a foreshock to a much larger earthquake later in the series of earthquakes. So now I'm going to show you recent earthquakes that have occurred in the United States. And this is just a map of, it's a U.S. Geological Survey map of the western United States here. And anyone can access it anytime to check out what sort of earthquakes have been going on. You can go to settings. You can change how many days you want to look at. You can see we're looking at 30 days, all magnitudes of earthquakes in the United States. And you can also zoom in to whatever area you'd like to look at. So let's take a look at Idaho here. It looks like we have a fair amount of earthquakes here in Idaho. And the orange is within the last day, yellow is within the last week, and white is within the last month. So you can see it looks like we're having a number of earthquakes around the Chalice, Idaho area here. Let's click on this one. So we had a magnitude 2.4, about 11 kilometers west-northwest of Stanley today. A magnitude 2.4, 23 kilometers west-northwest of Stanley today. And then a magnitude 2.5, 43 kilometers northwest of Stanley yesterday. And a number of others. And you can see that these aren't associated with a fault necessarily. I have all the fault lines drawn on here in red, as well as the tectonic plate boundaries. So over here to the west, you can see the Juan de Fuca plate where it subducts beneath the North American plate. And then further south here, you can see the San Andreas fault running through western California. You can see that there are a number of earthquakes in Washington and Oregon, most likely due to volcanic activity. A number of earthquakes along the San Andreas fault in California as a result of rocks on one side of the fault slipping past rocks on the other side of the fault. And then you have a number of faults that are not directly related to a plate boundary, but are just where rocks move past one another on either side of a weak point in the Earth's crust in Nevada and Utah here. And you can see that these earthquakes are typically occurring along these faults. Speaking of earthquakes being most commonly associated with plate tectonic activity, this shows earthquake distribution throughout the world, not just in the western United States. And if you remember where plate boundaries are, or if you simply note where the Pacific plate exists and how many earthquakes occur along the edges of the Pacific plate, where it's subducting beneath continental plates, then you may note that there are an extreme amount of earthquakes that occur along these plate boundaries and not nearly as many earthquakes that occur significantly inland. Speaking of tectonic activity and faults, let's talk about different types of faults and what types of earthquakes they can produce. So first, convergent plate boundaries, where you have two plates running into one another. These can produce the most powerful earthquakes. And in a subduction zone, for example, say the Juan de Fuca plate subducting beneath the North American plate, the boundary between the subducting and overlying plate is called a megathrust fault. And if it helps you remember, megathrust fault those faults are associated with the most powerful earthquakes. Moving on to transform plate boundaries. Let's talk about the San Andreas Fault as an example of a transform plate boundary, because it's a particularly large transform plate boundary. And along the San Andreas Fault, like other large transform plate boundaries, some portions of the fault exhibit slow, gradual displacement known as fault creep. And other segments of the fault regularly slip, where one side of the fault, the rocks on one side of the fault move relative to rocks on the other side of the fault, producing small earthquakes. And then you also have small strike slip faults that are associated with divergent plate boundaries. So if you recall at the Mid-Atlantic Ridge, for example, which is a divergent plate boundary, you have a number of small strike slip faults associated with that ridge that can also produce earthquakes. And I compare strike slip faults to transform plate boundaries here because the plate motion because the way that the rocks move on one side of the fault relative to the other is the same between strike slip faults and transform plate boundaries. So let's zoom into one of these megathrust faults. Again, here you can see a subducting plate subducting beneath an overriding plate, and you can imagine that there's a frictional force between the overriding plate and the subducting plate that's holding rocks on either side of that fault, or on either side of that megathrust fault, in place. Then when there's a slippage along that plane, you might produce an earthquake because of the release of energy. And the release of energy can be greater along a megathrust fault than it can a lot of other types of faults because of the nature of a subduction zone. So because there's a subducting plate that's moving further down towards the mantle, it is warmer and therefore more elastic, and so the amount of bend that those rocks might exhibit before there's a slippage along that megathrust fault is a greater amount of bend, which results in a greater amount of elastic rebound when there is a slip along the fault line, and therefore a larger earthquake than at other types of faults. Speaking of megathrust faults and the large earthquakes that they can produce, let's talk about a specific earthquake that happened in 2011 along a megathrust fault. So the country of Japan is located just 200 kilometers, or about 124 miles west of the Japan Trench. And at the Japan Trench, the Pacific Plate is subducting beneath the Eurasian Plate. And this subduction zone experiences frequent and large earthquakes. So on March 11th, 2011, the strongest recorded earthquake to hit Japan occurred. It was a magnitude 9.0 earthquake. This magnitude was significantly greater than was actually considered possible along this fault line. The energy released from the earthquake was about 600 million times more energy than the bomb of Hiroshima, the atomic bomb. Well-engineered buildings in Japan fortunately helped to reduce the loss of lives due to structural collapse. And the greatest loss of life was unfortunately due to the tsunami that occurred as a result of this earthquake happening beneath the ocean. So this map shows the focus of the earthquake, or the epicenter of the earthquake, which is just west of the Japan Trench there. And then on the island of Japan, you can see a number of dots that represent the intensity of shaking that occurred during the earthquake. So this intensity scale is called the Mercalli intensity scale. And you can see in some of the cities along the coast there, you had what is described as violent shaking, which produces heavy damage. And a lot of places that had severe shaking, which produces moderate to heavy damage as a result of this earthquake. So I'm going to show a few videos just to show you what the shaking actually looked like when this earthquake was occurring, so you can get a feel for what a very large earthquake actually looks like. So the first video that I'm going to show you is just what it looked like inside a supermarket in Japan when the Tohoku earthquake was occurring. Terrifying, right? And also terrifying that they would ask their employees to try to hold stuff on the shelves so it doesn't fall off and put their bodies in harm's way. This is a video of just like a clothing and shoe store during the earthquake. I don't know about you, but I would not want to be in that store when that was happening. And then finally I'll show you what some of the buildings in Japan looked like during the earthquake. So, as I said before, fortunately their buildings were constructed in a way that they were meant to live up to earthquakes and be able to continue standing, which means that they're essentially very elastic and not very brittle. So you'll see the building swaying in this video. Pretty trippy, right? It's really intense seismic waves produced from the elastic rebound during the Tohoku earthquake generated this magnitude 9 earthquake and led to some of the rather extreme intensity of shaking in some locations in Japan. So studying these earthquake waves or these seismic waves dates back to 2,000 years ago when Chinese began studying earthquakes. And the instruments that record seismic waves are called seismographs. And seismographs record the movement of Earth in relation to a stationary mass on a rotating drum or a magnetic tape. It's important to have the stationary mass as a standard to compare against, because how do you know how much shaking is occurring when everything around you is shaking and you don't have anything to compare it against? So this is a really old school seismograph here, but it shows you kind of the principle of a seismograph where you basically have a pen or a pencil coming down from something that's extremely stationary, and then the horizontal ground motion is recorded on the piece of paper as the ground shakes. So as the bedrock moves back and forth, for example, then that's recorded on the piece of paper or recorded on this seismograph as a whole. So let's talk about the different types of seismic waves that are produced by earthquakes, and what those different types of seismic waves can tell us about Earth's interior. So one type of seismic waves are called body waves, and these waves travel through Earth's interior. There are two types of body waves based on the mode that the wave is traveling through Earth. There are primary or P waves as the first type. Primary or P waves propagate through the Earth with sort of a push-pull motion or a compress and expand motion that changes the volume of the intervening material or the material that the wave is moving through. So when the material that the wave is moving through is being compressed, it shrinks the volume, and when it's being expanded, it increases the volume. P waves travel through solids, liquids, gases, anything, any type of matter. And generally, in any solid material, P waves travel about 1.7 times faster than secondary waves. So on to secondary or S waves. In contrast to P waves that have sort of a compression and expansion propagation through Earth, secondary waves create a shaking motion at right angles to their direction of travel. And S waves travel only through solids. They don't travel through liquids or gases or other types of matter. And they have a slower velocity than P waves. As mentioned on the previous slide, P waves are about 1.7 times faster than S waves. And they have a slightly greater amplitude than P waves, meaning that the shaking motion at right angles to the direction of travel of the S waves is slightly greater than the amplitude of the P waves. So I'm going to use a slinky for P waves and a rope for S waves to better explain to you exactly how these waves propagate through the Earth, so that you can later understand what these waves can tell us about Earth's interior. So if you think about a toy slinky at rest, if you're to push on it, it causes a compressional force, and then a wave would propagate through that slinky where you have alternating compression and expansion. And so the particle motion is parallel to the direction that you push the slinky. That is what a P wave is like. Alternatively, an S wave, if you imagine that you have a rope just at rest that you're holding away from a nail that is attached to on the wall, and then you shake the rope, you can see that the wave direction of the S wave is perpendicular to, or at a 90-degree angle to, the direction that the wave is propagating. So the wave would propagate from where your hand shook the rope towards where the rope is tied to the wall. And so it forms sort of an S shape as the particle motion is 90 degrees to the direction of propagation for the S waves. So again, P waves and S waves were body waves, or waves that move through the body of the Earth. But there are also surface waves. Surface waves travel along the outer part of the Earth. and they have a pretty complex motion as they do so. Surface waves cause the greatest destruction from earthquakes, so damage to buildings, infrastructure, etc. is usually due to surface waves, not P waves or S waves. And surface waves exhibit the greatest amplitude and the slowest velocity. So generally, the slower the velocity, the wave, the greater the amplitude. And the surface waves also have the greatest periods, or the largest time intervals, between the crests of the wave, or the peaks of the wave. Alright, so let's look at a diagram of the Earth and dissect how P waves and S waves, both types of body waves, and surface waves propagate through the Earth. So you have the hypocenter here, or also known as the focus, and then you have waves propagating away from that focus, or that area where you had elastic rebound and an earthquake occurred beneath Earth's surface, and those waves are propagating away in all directions. And then you have 3 seismograph stations that are measuring the earthquake, one fairly close to the epicenter, one fairly far away from the epicenter, and one really far away from the epicenter, seismograph 3 in that case. So if you're looking at the seismograph at seismograph station 1, you can see that the P waves arrive first. That makes sense because P stands for primary, and they arrive first, again about 1.7 times as fast as the S waves. The S waves, or secondary waves, arrive second, and then the surface waves arrive third. And you can see that the surface waves have the largest magnitude, or that the pen or pencil on the seismograph moves to the greatest degree when the surface waves arrive. And again, this is the reason why surface waves cause the most destruction on Earth's surface. If we move to seismograph station 2, we can see that the P waves still arrive first, the S waves arrive second, and that the proportion, or the P waves arriving about 1.7 times faster than the S waves, remains the same. And the magnitude of the surface waves is less than it was at seismograph 1. So as you might imagine, the further you get away from a focus or an epicenter, the less the less great the magnitude of the surface waves, or the less destruction that you might see on the surface of the Earth. Then if we move to seismograph 3, we can see that the P waves have arrived, and the S waves and the surface waves have not yet arrived. So this seismograph 3 is extremely far away from where the earthquake occurred, and it's just going to take longer for the S waves and surface waves to get there. Now, there are actually 2 different types of surface waves, which we haven't discussed yet, and I'm going to go through an animation here that will explain these 2 types of surface waves to you. Now, there are actually
Earthquake
2
waves.
Different types of
the energy
surface waves,
released during an earthquake
moves
through the ground in the form of earthquake waves. These waves originate at the center of fault movement, known as the focus of an earthquake. The strongest shaking of an earthquake is often experienced on the ground directly above the focus, at the location known as the earthquake epicenter. Fault movement produces several different kinds of earthquake waves. Waves that move through the interior of Earth are called body waves, while those that travel only around the surface of Earth are called surface waves. The fastest moving earthquake waves and the first vibrations to be felt during an earthquake are known as primary, or P waves. Notice that the P waves move through the ground in much the same way that sound waves move through the air, by alternately compressing and relaxing the medium through which they are traveling. The initial jolt of the P waves is followed by the strong side-to-side and up and down shearing motion of the slower-moving secondary, or S waves. Notice that the pattern of ground movement caused by S waves is quite different from that of P waves. As S waves travel through the Earth, the ground moves up and down or shakes from side to side. Surface waves typically arrive immediately after the S waves. They move around the surface of Earth in much the same way that ocean waves move through water. Notice that the wave motion does not extend very far below the surface. Vertical surface waves often produce the rolling motion experienced during a large earthquake. Surface waves may also move horizontally. Notice again that the wave motion does not extend very far below the surface.
So seismographs aren't only used to tell us something about the magnitude of the surface waves or the magnitude of the P waves or S waves or when any of these waves arrive. They're also used to determine where the source of the earthquake actually is. We can use seismographs to determine the geographic epicenter or the location on the surface of the Earth above where the earthquake occurred. And we can determine the travel time to each seismic station based off of when the P waves, S waves, and surface waves arrive. And we can use 3 seismographs to triangulate the origin of the earthquake. So for example, if an earthquake occurs and you have 3 seismograms, one in New York, one in Alaska, and one in Mexico City, and you track when the P waves and S waves arrive, then you can plot when the P waves and S waves arrive on a graph where you have basically the distance from the epicenter in miles plotted against the time in minutes since the earthquake occurred. And so this can tell you how far away, using both the P wave and the S wave, how far away each of the seismograph stations is from the epicenter. And so if you have 3 seismograph locations, then you can triangulate the location of the epicenter. So we have that seismograph station in Nome, Alaska, and in New York, New York, and in Mexico City. And we look at the difference between when the P waves and S waves arrive to get a geographic distance that each seismograph is from the epicenter. And then we draw a radius that aligns with the distance from the epicenter, a radius from going from each seismograph station, and all 3 seismograph stations in this case converge upon the location in the United States where the earthquake came from. Now, when you talk about an earthquake size, how big of an earthquake it is, there are really 2 ways to describe that, and both of which I've already alluded to some extent. But to clarify, the intensity of an earthquake is a measure of the degree of earthquake shaking at a given location based on the amount of damage that occurs. And the magnitude of an earthquake estimates the amount of energy released at the source of the earthquake. It's important to note here that the magnitude of the earthquake is sort of a universal measure of the amount of energy released by the earthquake, whereas the intensity of the earthquake is dependent upon the geologic properties of the location that you're talking about. So for example, you might have one location that's 50 miles away from the epicenter of an earthquake that has low intensity, and another area that's 50 miles away from that same earthquake that has a high intensity. and that is due to differences in the geologic material of those two locations. So the intensity scale most often used for earthquakes is called the Modified Mercalli Intensity Scale. And it was developed using California buildings and the damage that occurs to California buildings following earthquakes as its standard. The drawback of intensity scales, obviously, is that destruction of buildings may not be a true measure of the earthquake's actual severity, right? So if we think back to that Tohoku earthquake, and you saw how the skyscrapers in nearby cities in Japan were rocking back and forth in a crazy way, well, there wasn't a lot of destruction to those buildings from that earthquake, even though it was a magnitude 9 earthquake. And that's because those buildings were very well constructed in anticipation of having to stand up against earthquakes.
Hi there, Callan Bentley back once again for another Smart Figure. In this video we're going to take a look at earthquake intensity and magnitude. After watching the video you should be able to distinguish between those two and calculate the magnitude of an earthquake using a seismogram. Let's begin with intensity. Intensity is basically a measure of the quality of the shaking during an earthquake. And this is based on interviews with people afterwards and observations of the structures like buildings, whether their foundations were cracked or they lost their chimneys, that sort of thing. This is an intensity map for an earthquake that took place near Santa Cruz, California. And you can see that the darker colors correspond to higher intensities and the intensity diminishes with increasing distance away from the quake. Here's another map showing intensities for two different quakes. One is a magnitude 6 quake that occurred in Central California in 2004, and the second is a smaller quake, magnitude 5.8, that occurred in Central Virginia in 2011. Now you can see here that the Virginia quake was felt over a much broader area than the California quake, and that basically has to do with the fact that the crust is much colder in the eastern half of the country, so seismic energy is transmitted much more efficiently over a greater distance. And as a result, this Virginia quake, even though it was only a 5.8, was felt probably by more American citizens than any other earthquake in history. Now sometimes we have an earthquake occur in a place where there are no people to report on the shaking, or there are no buildings to have their chimneys snapped off. And so we need a better method for determining how strong an earthquake is. Charles Richter developed such a method, and it basically uses information from a seismograph. So we take a look at this seismograph and we can measure the S minus P time, which is basically correlating to the distance away from the earthquake, and we can plot that on the left axis. Then we measure the height of the maximum S wave, so how far away from the center line the maximum S wave got. In this case, it was 23 millimeters away. We plot that over on the axis on the right. Then we've got two dots, and we can unleash our inner kindergartner to connect those two dots. The line that connects those two dots crosses a third axis in the middle, and that spot where it crosses that third axis is the magnitude of the quake. So in this case, it's Richter magnitude 5. We call that ML. What we can do now is we can take away some of this other information and pretend we've got that same quake, but we're going to go ahead and look at what that same quake feels like from a greater distance. Let's imagine we're 400 kilometers away from that same magnitude 5 quake. What's going to be our maximum amplitude of shaking? Well, once again, we draw a line. That line connects the 2 points that we know about, and it ends up giving us a maximum amplitude of around 3 or 4 millimeters of shaking. We actually end up using moment magnitude rather than Richter magnitude for most earthquakes because it ends up being a more robust scale at the very high end. The Richter magnitude breaks down for really big earthquakes. Notice here that as earthquake magnitude increases, we see that there are fewer and fewer of them per year, and that the larger magnitude earthquakes end up releasing a tremendous amount more energy. Each step up on the moment magnitude scale corresponds to a release of about 32 times as much energy. Okay, time to test yourself. Let's go ahead and imagine that you're 40 kilometers away from a magnitude 3 earthquake. What's going to be your amplitude of shaking? Draw draw the line. That line ends up connecting to our third axis and suggests that we're going to have around 3 or 4 millimeters of maximum amplitude S-wave shaking. You probably got that. It's pretty easy to connect 2 dots and extend that line over to create a third dot. That's all you have to do. Thanks very much for your attention. This has been another Smart Figure.
So this slide just shows how often earthquakes of different magnitudes occur, what happens when an earthquake of that magnitude occurs, some examples, and how much energy is released. So you can see that anything above a magnitude 9 earthquake typically happens less than once a year and releases the equivalent of 56 trillion kilograms of explosive in energy. And so these are the largest recorded earthquakes of all time. And they destroy structures over a vast area and can lead, unfortunately, to massive loss of life. Some examples were a couple of earthquakes in the 60s in Chile and Alaska, and then the 2004 Sumatra earthquake, and then the 2011 Japan earthquake, which I talked about earlier in this lecture, the Tohoku earthquake. And then it's important to note that when you move down to a magnitude 8 earthquake, that still only occurs about once a year. So those are still very severe, like the Chile earthquake in 2010 or the Mexico City earthquake of 1980. And then when you get down to the 6 range, there are only about 134 of those a year. So that recent large earthquake out of the Chalice area that many of you probably felt, that was in the 6 range, and there are only about 134 of those per year in the world. And then anything below a 2 is generally not felt by humans, and that's why there aren't examples of those earthquakes on this chart here, is because I guess we generally don't care about earthquakes of a magnitude too small to feel. Imagine that. So combining the magnitude of the earthquake and the intensity of the earthquake, you can get at how much destruction might be caused by the seismic vibrations. And the amount of damage to structures or the destruction caused by these vibrations is a function of the magnitude of the earthquake, as you might imagine, the proximity to the epicenter. So the closer to the epicenter you are, the more destruction is likely to occur. The earthquake intensity, which again is related to not only the proximity to the epicenter and the geologic material in that region, but also the viability of the structures there, because the intensity is a measure of the damage to the structures. The amount of damage is also a function of the duration of the vibrations. The longer they go on, the more damage might occur. And I guess I already addressed the other two. So speaking of the geologic material impacting the amount of damage caused by seismic vibrations, soft sediments amplify seismic waves more than solid bedrock. So if you go back to that example where we had similar magnitude earthquakes in California and Virginia, you'll notice that folks felt the earthquakes further away in Virginia, but the damage to structures was likely greater in California because of the softer sediments and softer bedrock in the California area. And another factor that can increase the destruction of an earthquake is liquefaction of the ground. And liquefaction is when unconsolidated materials saturated with water turn into a mobile fluid. So you can think of this as a sand, for example, with water in it, might all of a sudden turn into a fluid and flow as such. So this actually happened after one of the larger earthquakes in the Chalice area. If you go to Stanley Lake and you hike the trail near the parking lot at Stanley Lake, you will notice some educational signs that show that some of the sand that was adjacent to the lake itself experienced liquefaction, and you had trees that were once rooted in the sand that just sunk into the earth and are now out in the middle of the lake or completely buried, and the lake now extends further than it used to because some of the sand, as it flowed like liquid, just sunk into the earth as a result of this liquefaction. Other ways that earthquakes can become more destructive are by landslides and ground subsidence. So the shaking of the ground causes loose sediments on a slope to slump or to move down slope as landslides. And ground subsidence can occur because you're shaking the sediment, so sediments may move down to fill in gaps that are exposed in the sediment due to that shaking. Earthquakes can also cause fires, so especially near human structures, earthquakes can rupture gas and electrical lines and start fires. And in addition, earthquakes can break water lines, which can make fire control problematic after the earthquake already started the fire. Earthquakes can also cause tsunamis or seismic sea waves. So in the case of the 2011 Tohoku earthquake, what I didn't show you is that it also caused a massive tsunami to crash inland into Japan. And the tsunami is actually what claimed the most lives rather than the earthquake itself. So tsunamis result from vertical displacement along a fault located on the ocean floor or a large undersea landslide triggered by an earthquake. And in the open ocean, the height of a tsunami is usually less than a meter. So if you're, for example, on a boat out in the open ocean near where the Tohoku earthquake occurred, you might not even notice that there was a tsunami heading inland towards Japan because the height change in the ocean was less than a meter there. However, once the tsunami reaches shallower coastal waters, the water piles up to heights that occasionally exceed 30 meters, and that can obviously be very destructive. It's pretty bad when you see a building floating away. So this is just one location, but this happened all along the coast. So that concludes my presentation for this week. I'd like you to please read more about tsunamis in your textbook. and also read about Earth's interior and what seismic waves from earthquakes tell us about the characteristics of Earth's interior. And I will include questions on these topics in your reading quiz. Thanks, and hopefully I'll speak with you in office hours, and if not, I look forward to another lecture next week. Talk to you then. Thanks. Bye.